Our first mini course today is by Ruadhaí Dervan from University of Warwick, and he's going to tell us about Z-critical connections and stability. Over to you, Ruadhaí.
Great, thanks a lot for the invitation. It's great to be here. I'm going to try and take the pedagogical component kind of seriously. So especially, please do ask questions if you have any, and please shout. It's a big lecture theater. I'm kind of amazed by the size of this blackboard, so if I do something wrong as well, please tell me. Okay, so the title is Z-critical connections and stability conditions. It's a team of research I've been developing over the last maybe 5 years in collaboration with a few people in a few different papers. So these are Michael Hallam, John McCarthy, and Lars Sekton. So I'm going to begin with some motivation that will be much more like big picture mathematics, before then returning to some foundational actual details, especially on the language of complex geometry. So the motivation is the following. Okay, so one of the major themes of complex geometry, so this will really be a mini course in complex geometry and in Kähler geometry. And one of the major themes is the interplay between two different things. So complex geometry, you can think of it as sort of like the study of algebra geometric objects, but using the language of differential geometry. So a major theme of complex geometry is really the interplay between these two sides. So this is the interplay between, on the one hand, you have the sort of pure differential geometry style of question. So that will be, on this side, solvability of certain geometric PDEs, which give you something natural and interesting on the differential geometry side. So these are PDEs determining canonical metric structures on the objects that you might be interested in. So determining natural or canonical metric structures. So these are PDEs for metrics in various categories. Okay, so you should have in mind, maybe I might be thinking about Hermitian metrics on vector bundles. That will be really what the course is about. But you could be thinking about Kähler metrics on complex manifolds or something else. So on bundles, holomorphic vector bundles, or manifolds, complex manifolds. The question makes sense in some generality. And the theme is that this question, which is really an analytic question, it's a question that lives in differential geometry or geometric analysis. And the theme is that there's a deep connection between this side of the picture and the purely algebra geometric side of the picture. So this will be algebra geometric stability conditions. I guess many of you will be familiar with roughly what this means on this side. At least you'll know what a PDE is. Whereas stability condition may not be something that all of you have encountered before. What's important here is really the first two words, algebra geometric. The point is that these are natural geometric questions that are kind of geometric analysis that we can try to connect to algebraic geometry and to try to answer through algebraic geometry. I think that the most classic incarnation of the story is one that goes back to the 1980s, really, at this stage. So that's called the Hitchin-Kobayashi correspondence. I suspect we'll hear many things about this, especially in its Higgs bundle setting. The Hitchin-Kobayashi correspondence. Okay, so here we're in the setting of holomorphic vector bundles, and we try to connect the natural metric structure of vector bundles to an algebra geometric stability condition. And this says that the existence of a Hermite-Einstein metric, this is a geometric PD for a Hermitian metric on a holomorphic vector bundle. So on a holomorphic vector bundle. So the correspondence says that one can find such a thing, namely one can solve this geometric PD precisely when the vector bundle satisfies an algebra geometric condition, which is called slope stability. So here we fix a given vector bundle, which I'll call E, and then we ask for this algebra geometric stability condition to hold for E itself. I'll explain what both of these are later in this talk, or possibly maybe at the start of the next talk if things go slowly. But I want to just explain why we might be interested in such correspondence before going much further. So there are really many reasons to be interested in such correspondence that come from different parts of geometry and different parts of mathematics. So many reasons to be interested. And I think which you find most compelling is probably dependent on which part of mathematics you come from yourself. I really mostly come from algebraic geometry in some sense. And there, the major motivation is to moduli theory. This is really one of the basic questions in algebraic geometry is, can we construct moduli spaces? And roughly speaking, one should imagine the answer to that question is that one can construct moduli spaces, not of everything that you're trying to parameterize. So again, you should imagine maybe you're trying to parameterize vector bundles over a curve or a higher dimensional variety. But one can only construct moduli spaces that actually parameterize stable, really polystable objects. So what does this say in the setting of the Hitchin-Kobayashi correspondence? It says that, imagine we fix some compact complex manifold, for example, a smooth projective variety, and we're interested in classifying vector bundles over that variety or that manifold. Then this philosophy would say that we should be able to construct moduli spaces, not of all of them, but only of the stable ones. But then that says that we should also be able to do this using this theory of Hermite-Einstein metrics. So these correspondence says one thing that they're doing is that, in particular, they give an analytic structure to moduli spaces. So they give an analytic approach to actually constructing moduli spaces. But then they get extra structures. When you construct a moduli space in differential geometry, you get extra differential geometric structure. So we get an analytic approach to constructing moduli spaces. And in particular, they give these moduli spaces extra structure, analytic structure, for example, natural metric structures. Extra analytic structure. Okay. So moduli theory being very fundamental in algebraic geometry, this is probably, for me, the most compelling reason to be interested in this sort of correspondence. I'll mention some others that come from slightly different perspectives. A frequent one is enumerative geometry. So in algebraic geometry or mathematical physics, we often want to count things. It's a prominent theme. So one can use moduli spaces, but we learned that to construct moduli spaces, we should restrict what we're actually parameterizing to these stable ones. So one can use moduli spaces to count things. And what it is that we're counting is probably too broad to specify in any generality. But I'll mention maybe one of the more classical examples was, for example, curves of certain type in your variety or in a complex manifold. Or you might try to count certain types of bundles with certain properties as well. But usually these enumerative invariants are defined as something, it's a first approximation, something you should imagine as an integral over a moduli space. So this sort of all builds up from this moduli theory, which builds up from this sort of story. And this was one of the classic examples of an application of the Hitchin-Kobayashi correspondence. Okay. So in practice, I think a lot of the people interested in these correspondences instead come from geometric analysis or PDE theory, in that algebraic geometry in particular, it can lead you to try to derive the Hermite-Einstein equation from one perspective. And so algebraic geometry can be used to suggest interesting geometric PDEs. So algebra geometric stability conditions. In geometric analysis, it's not difficult to write down a PDE. It's difficult to write down a PDE with interesting properties. So algebra geometric stability conditions, these can actually lead to interesting, i.e. geometric PDEs that actually have strong geometric properties. So it can lead to interesting geometric PDEs. And there are many examples of this. Many different parts of mathematics. Okay, and also there are many other reasons that I won't really get into, but one could be motivated by questions in mirror symmetry, which is itself kind of close to mathematical physics, or one could also be motivated by genuine mathematical physics as well. So these are rich questions because they touch upon many different parts of mathematics. Okay, so this Hitchin-Kobayashi correspondence, I'll just mention this is sort of a 1980s story at this stage. What happened was the theory of slope stability. Well, I think we've proven almost everything we would like to know about slope stability, and we proved these results quite a long time ago. But there is a rich theory of extensions or modern ways of viewing the sort of structures that live in the theory of slope stability of vector bundles that are very prominent in modern algebraic geometry. So in algebraic geometry, roughly speaking, motivated by questions in mathematical physics, the general theory or the structures involved in the theory of slope stability, which remember this is a stability condition for vector bundles, this led to a more homological theory, to what are called Bridgeland stability conditions. Okay, and so one of the points of Bridgeland stability conditions is that they live in homological algebra. They give a notion of stability that is defined on general triangulated categories. So these give, in particular, a very flexible notion of stability, i.e. there have been many Bridgeland stability conditions. But they live much more in homological algebra. So really they live as stability conditions on triangulated categories. This being a course in Kähler geometry, I'm not really going to talk about the homological algebra so much, but the example you should keep in mind is the derived category of coherent sheaves on a projective variety. So things here are just homological generalizations of the notion of a vector bundle. First of all, we extend vector bundles to sheaves, coherent sheaves. Then we allow complexes, as we might be familiar with from different parts of maths. And then we just consider complexes up to quasi-isomorphism. So we just kind of consider an equivalence relation and mod out by it. Okay, and so on one hand, we've generalized to some setting that's kind of abstract and one that I won't really go into. But the point is that it becomes much more powerful. So actually, in some sense, this setting is really the most natural setting for stability in these kind of linear settings. the motivational point is that we get, in this context, whilst slope stability was roughly speaking the only natural choice one could make at first, in this side of Bridgeland stability conditions, we actually get many choices of stability conditions. We get many stability conditions, but in some sense, finite dimensional. So stability conditions, they're parameterized by topological information, essentially. So parameterized by, in fact, a finite dimensional complex manifold. So in particular, we don't get a natural choice. So in the theory of slope stability, there was a natural choice. Here we get many choices, but one of the benefits then is that we can vary the stability condition. So varying the stability condition is really what led to many of the applications. So the stability condition, this is really behind many of the applications of this whole story. So it's behind really much of the interest. And especially of the applications. Okay, so this leads then naturally to the motivational goal for this mini course. So, question. So can we define PD counterparts to Bridgeland stability conditions? Okay, so what does that mean? We would like some kind of flexible notion of a geometric PDE that makes sense in such a way that solvability becomes equivalent to existence through some generalization of the Hitchin-Kobayashi correspondence, motivated by the many applications of Bridgeland stability conditions. So with stability still being the same as existence of solution. Okay, so I'll say right from the start that this is probably too ambitious for 2026, but just in terms of motivation, so as with all of the motivation, this would, for example, give an analytic structure to the moduli spaces that are of interest in algebraic geometry of these moduli of Bridgeland stable objects. So this would give analytic structures, for example, to resulting moduli spaces by this kind of general philosophy. Okay, so again, this is probably too ambitious. What do I mean by this? What I mean is that we haven't solved this problem yet. So I'll add a caveat that this is really, I'd say it's too ambitious for now. It seems like a completely reasonable thing to try to do, but I won't succeed in doing that in the next 3 hours. So instead, so we try to at least begin some kind of program to get this story started. So we try to begin answering this question. But rather than this homological setting of the derived category of coherent sheaves, I'm just going to stick to holomorphic vector bundles. So in the simplified setting, of vector bundles. So in some sense, this is really the motivational goal. We haven't got there yet, but we want to try to implement the sort of structures that one sees in the theory of Bridgeland stability conditions in such a way that we can write down sensible geometric PDEs, but more flexible ones for Hermitian metrics on holomorphic vector bundles. Okay. So for vector bundles, but again, with respect to more general stability conditions, so we want a kind of flexible notion of a geometric PDE for a Hermitian metric on a holomorphic vector bundle. That's roughly speaking what we've achieved as of now. Okay. So the next thing to do is just to sketch a brief outline before returning to specifics and concrete details, really a review on complex geometry. But are there any questions on the motivation for now? I'd be happy to take any. Yeah.
So these moduli spaces are known to exist as coarse moduli, or?
Yeah, I mean, well, there's this general story of, so first of all, it's not an easy thing to do, but it's been achieved in large generality to construct a Bridgeland stability condition on the derived category of coherent sheaves. But once you have one, there's some general machinery that gives you moduli spaces. So you get this notion of a good moduli space of the stack parameterizing semi-stable objects. But yeah, you can kind of think of it like a coarse moduli space, yeah. Yeah, so when I say you should get analytic structures on the resulting moduli spaces, we don't really have a good way of thinking about the analytic structure of stacks yet. And so one should imagine that what I'm talking about is really kind of resulting coarse moduli spaces. So we've really got an algebraic variety or something where we can talk about what a Kähler metric means on an algebraic variety. Yeah. Any other questions?
Hello, sir.
Oh, yeah.
Could you briefly describe that what is stability? Like, what's the definition of stability?
Oh, yeah. So we'll do outline, and then we'll do brief review on complex geometry, and then I'm really going to define what slope stability is. So I think if you would like to have some kind of very rough idea, it's a numerical condition, i.e. it involves inequalities of numbers, where the inequality is associated to, you associate a topological invariant to your vector bundle and a topological invariant to subbundles or subsheaves. That'll be the flavor. So it's something quite concrete in practice. In different settings, if you're talking about geometry of manifolds, you have to do something a little bit different. Yep. Okay, great. So outline after motivation. So I'll give a very brief review of complex geometry. The basic definitions and ideas of complex geometry. And secondly, then I'll talk in detail about the Hitchin-Kobayashi correspondence, or at least enough to let you understand what Hermite-Einstein metrics are and what slope stability really is. So Hitchin-Kobayashi. Correspondence. Okay, and then I'll talk about a sketch of why connections between algebraic and differential geometry actually exist. That's the theory of moment maps and geometric invariant theory in algebraic geometry. Okay, and that will be enough to motivate why we might be reasonably able to write down more flexible geometric PDEs for Hermitian metrics on vector bundles. So that will lead us to this theory of Z-critical connections. These are a flexible geometric PDE for a Hermitian metric, or equivalently a connection on a vector bundle. And moment maps, so I'll explain how to derive these equations. And then likely lastly, what I'll talk about is sort of a Hitchin-Kobayashi style correspondence for these more general geometric PDEs, a correspondence of this sort of class. Not in general, but in what I'll call the large volume regime. Okay, and I would be amazed if I get any further. There are two bonus topics if I do. One of them is about the deformed Hermitian-Yang-Mills equation, which is a very rich theory in a special case, a very rich special case of this theory. The other is about applications to the metric geometry of moduli spaces. If either of those sound interesting to you, I think I'd be amazed if I get to them in the actual lectures, but feel free to ask me about them over coffee or lunch or somewhere. Okay, great. So next up is a very rapid review of the basic structures of complex differential geometry. So I'm going to talk a little bit about Hermitian metrics, curvature, and that sort of thing. So complex geometry. I'll rudely erase my collaborators as well. Okay, so I expect many of you will have seen these definitions before, so I'm going to go quite quickly because I think the theory of complex geometry merits a full lecture course itself of much more than 3 lectures. So what I'll be doing is just reminding some of the basic definitions. But there are many nice books to familiarize yourself with these ideas. So we consider complex manifolds. I'll usually write as X. These are just like smooth manifolds, except we require instead the charts to be of the form mapping open set in X to open set in Cn. And then there's a natural notion of a holomorphic map between open sets in Cn to open sets in Cn. We just require holomorphic and every variable with the others kept fixed. So we ask then that the transition functions are holomorphic. Okay, and somehow, of course, the point is not to say what the definition is, but what the properties are. And the point is that we really get a notion of a holomorphic function locally and globally. So we get notions of holomorphic functions. We can talk about holomorphic maps between complex manifolds, and so on. These are all well defined because of the way that we've defined a complex manifold, namely that we have holomorphic transition functions. So we reduce to complex analysis in the same way that differential geometry reduces to real analysis. Okay, so I imagine that's a notion that's familiar to many of you, but I'll give the main example. So X, a smooth variety over C, for example, a projective variety, then X can be viewed or is a complex manifold. So not all complex manifolds are projective or algebraic varieties. For example, I mean, the disk in C is certainly not an algebraic variety. And similarly, there are also compact complex manifolds that are not algebraic varieties. Okay, the main object will instead be really vector bundles, so E over X. So E, as in the definition of a smooth vector bundle, the total space is a complex manifold. We have a holomorphic map down to the base. So this is a vector bundle. So this is a vector bundle. So we just require that locally it's trivialized. As, of course, we just require the fibers to be CR instead of or. So U times CR over U. So R is rank. And we again require that the transition functions are holomorphic. So with transition functions, so these live in, for example, U intersect V into GL of OR-C. GL OR-C, that's a complex manifold because it lives in CR squared. And in particular, we can ask for the transition functions to be holomorphic. This is really copying the definitions from differential geometry and importing them into complex geometry. Okay, so the first difference is that a complex vector bundle, a holomorphic vector bundle, the fibers are complex vector spaces. And so the natural metrics on them, they're Hermitian metrics rather than just metrics, i.e. inner products on the fibers are varying smoothly. Okay, so the fibers, that's right, E sub x. So x is the point in x. That's the fiber over the point x. That's a copy of CR. These are complex vector spaces. So in particular, we can try to put Hermitian metrics on the vector bundle, which are just Hermitian inner products on the fibers varying smoothly. So we consider Hermitian metrics on E. And in particular, we would like to talk about curvature. So in differential geometry, one of the main things we're interested in is curvature. So we would like a notion of curvature that works in here. Usually we think of in vector bundle worlds, curvature is something that's associated to a connection. So what we do is associate to a Hermitian metric on a holomorphic vector bundle a connection, and then we define curvature associated to the connection. So a Hermitian metric H induces on this holomorphic vector bundle, it induces canonically a Chern connection. So roughly speaking, this plays a similar role to the Levi-Civita connection in Riemannian geometry. So nabla on E. So what does this mean? So nabla, it takes smooth sections of E and gives back a one form with values in E with this sort of like almost linearity property under multiplication by functions. So nabla of fs is equal to, so f is a smooth function on x, df tensor s plus f nabla s. So this is a sum of one forms with values in E. So that's just the definition of a connection. And what does it mean to be the Chern connection? What it means is that it's compatible with both structures that we have. On the one side, it's compatible with the fact that we have a complex holomorphic vector bundle. And on the other hand, it's compatible with the Hermitian metric. So, okay, so nabla 0, 1, i.e. we project onto 0, 1 forms. These are things locally of the form dz bar from A0, V. So this is 0, 1 forms. Again, like locally things, sums of the form dz bar, but with values in E. This 0, 1 projection is just the del bar operator. So this is a holomorphic vector bundle. If we've got a section of it, we can take sort of locally in coordinates and check that it's well defined. We can take del bar of it, and we'll get a 0, 1 form. Again, and del bar of it vanishes precisely when the section is holomorphic, which is can be familiar from complex analysis as a general idea of how things work in complex geometry. So that's something that makes sense because E is a holomorphic vector bundle. And what I said is that we also need compatibility with the Hermitian metric. And that's going to look, again, kind of similar. So D of S prime, if I've got two sections of my bundle, I can use the Hermitian metric to induce a function, which is just the pairing of these things. So it's a function, we can take its differential. And I ask that this is the same thing as, so this is a one form with values in E. S is a section of E. But we can use the Hermitian metric to get back a one form just by killing the two E components. And it should be symmetric. So we ask for this. So this is what it means to be a unitary connection. So that'll come up later as well. Okay, so the Chern connection is the unique connection that's compatible with both the holomorphic structure and the Hermitian structure. Okay, and kind of conversely, for E, a complex vector bundle, which means that I do not require the transition functions to be holomorphic, but it is something that has fibers that are complex vector bundle vector spaces. Okay, I can still make sense of a Hermitian metric. If I take a unitary connection, if I have a sort of integrability condition that the 0,1 component of this connection squares to 0, this is integrability, then actually we can upgrade E to a holomorphic vector bundle such that this is the Chern connection. So there exists a holomorphic structure on E with nabla then the resulting Chern connection. So it's often useful in this story to take two perspectives. One is to fix a holomorphic vector bundle and vary the Hermitian metric. The other perspective is to fix a complex Hermitian vector bundle and vary the connection. And this says exactly how they're equivalent, depending on how much you want to worry about this integrability condition. Okay, so the point of introducing connections is to differentiate, and differentiation leads to curvature. So when we want to talk about curvature, we require a connection, and in particular, we get connection in this category as well. So we get curvature FH or F nabla, which is just nabla squared. So this is a two-form with values in ND. So nabla squared, we have to upgrade what the connection does for one forms with values in ND, but there's a canonical way of doing so. And in fact, it turns out to be a 1-1 form with values in ND. So 1-1 form, locally it's a two-form that's of the form dz wedge dz bar for z some local coordinates. Okay. It leads to curvature, but maybe one of the most important aspects of this, at least when you take an introductory complex geometry course, is that this actually leads to natural topological invariance of the vector bundle as well through what's known as Chern-Bay theory. So this leads to Chern-Bay theory. So we try to understand characteristic classes of vector bundles through differential geometric input. So Chern-Bay theory. So what we do is we associate the Chern characters. So we associate a topological choice, topological output that is actually really a it lives in the corresponding cohomology of just differential forms that have like J holomorphic coordinates and J anti-holomorphic ones. And the way we do that is just by taking our curvature up to a normalization. We take the jth power of that. Where does that live? So that's going to be a J form with section or with values in ND because we just multiply on the ND component. We take 1 over J factorial, again, that's a normalization. And we take trace to give us a JJ form, which is what we claimed. And the claim really is that this is actually independent. The cohomology class of this thing is independent of the Hermitian metric, leading to topological classes associated to a vector bundle. So it's probably a little bit quick if this is your first time seeing characteristic classes, but nevertheless, this is the way it works from the differential geometric perspectives. These are called the Chern characters. They're completely equivalent in information they provide to the Chern classes, which are more common in some sense, but these are more convenient for our purposes. So these are the same information as Chern classes. The next thing that we want to do is just say a little bit about the metric geometry of complex manifolds themselves. So omega, so this sort of ends the period on vector bundles for the moment. So omega on X is a Kähler metric. So if omega is, first of all, a closed non-degenerate two-form, so this will be important later again. So this is called a symplectic form. So a Kähler metric is in particular a symplectic form with an additional condition that it's compatible with the fact that we have a complex manifold. So it induces a Riemannian metric. So with omega, so this is a two-form to take two tangent vectors and give you back a number. So if I do that on the first variable, but then I kind of use my extra structure that I have a complex manifold, that gives us an operator J, the almost complex structure, that looks like multiplication by I on the tangent spaces. That converts my skew symmetric two-form to a symmetric one. And I can ask that this is actually a Riemannian metric. So in some sense, probably historically, the way you would have viewed this is to say that you had a Riemannian metric that was compatible with the fact that you have a complex manifold. So that's roughly speaking what a Kähler metric is. So in particular, we get a Riemannian metric. So omega is then a 1-1 form by J invariance, which means locally, again, it's just of the form things like dz, wedge dz bar. So it's 1-1 form. And locally, so if I take a sufficiently small open charge, open set in X, so omega, again, just locally, it's of the form so complex Hessian of a function. So we get these operators del and del bar refining the D operator on a complex manifold. And locally, our Kähler metric is just the complex Hessian of a function, basically. Okay, and I just want to mention one final result before moving on from this very rapid review on complex geometry. Okay, so there's maybe something else to note is that because we have a symplectic form in particular, omega to the n, this is actually a volume form. So we have a natural volume form in Kähler geometry. And if you like Riemannian geometry, you could say, okay, well, what about the other volume form that we could have got from the Riemannian metric? And they turn out to be the same. Up to kind of dimensional scaling. Okay, yeah, and I just want to mention a theorem, which is the Kadara embedding theorem. So the point of mentioning this theorem is not that we really use it in the talk whatsoever, but rather many of you might be coming from an algebraic geometry background, where in algebraic geometry, you've got a positivity theory that's reflected in differential geometry and Kähler geometry. And this is sort of the first manifestation of that. So a line bundle on a compact complex manifold X satisfies the natural positivity condition in algebraic geometry, namely that it's ample. So what does this mean? It just means that there is an embedding of phi of X into Pn for some n, such that the pullback of the natural line bundle on Pn, the dual of the tautological bundle, namely the hyperplane bundle, is just L, at least up to a tensor power. So with L being isomorphic to the pullback of O of 4, O of 1, and I tensor this by L, or somewhere. I.e., this is a line bundle that induces embeddings into projective space. Okay, so this is the first half. So this is our line bundle is ample. That's an algebra geometric condition about embeddings into projective space. If and only if. Okay, so a line bundle also has a Chern class. Chern character, first Chern character. This admits a Kähler metric. Okay, so part of the definition of a Kähler metric is that it's a closed form. So in particular, you get a class in H2 of XOR, but I said that omega is locally, it's a 1-1 form. So we get a class in H11 of XOR, which is exactly where this lives as well. So at least it makes sense to ask this question. And this is really saying that the positivity condition in differential geometry is matched by that in algebraic geometry. So when I'm choosing a Kähler metric, cohomologically, just what I'm doing, you should imagine, is choosing an ample line bundle. But I don't really need to restrict myself to projective varieties to make sense of this. So, and particularly, this all implies that X is projective. Okay, so once I can find a Kähler metric in the first Chern class or Chern character of a line bundle, I must be projective. Okay, Yeah, great. I realize that's probably a little bit too rapid for those of you who have not been exposed to these ideas before. But I hope for those of you who have been, but maybe some number of years ago, this has at least refreshed your memory on how some of these things work. So from here on out, I'm going to be fairly freely using the language of complex geometry. Are there any questions on this sort of introductory material on how we use the language of complex geometry? Okay. Yeah, feel free to ask questions over coffee or something, especially about this introductory material. Okay, so what, I have something like 5 minutes left. Is that roughly 10 minutes? Okay. Great, okay, so then I may achieve my ambition of giving some more precise details on the Hitchin-Kobayashi correspondence. So the Hitchin. Again, you'll remember this is linking the metric geometry of vector bundles, which we now have some idea of what it means, to the algebraic geometry of vector bundles through this notion of slope stability. So the question that one can ask is, okay, so a vector bundle admits many Hermitian metrics. It's an infinite dimensional space, just because, I mean, it's completely analogous to the fact that a complex vector space admits many Hermitian inner products, and we're just varying those choices fiber by fiber. So a holomorphic vector bundle this admits many Hermitian metrics. So one can ask the natural question, is there a natural choice, or is there a canonical choice of such a thing? So is there a natural or canonical choice? And this is very similar to questions that we ask in many different parts of maths. Okay. So what we want to do is define a geometric PD that will determine one, where natural or canonical means that we have some kind of uniqueness theory. Okay, so we'll let X omega be compact Kähler, so omega is a Kähler metric. E over X holomorphic vector bundle. Okay, so in particular, we know what it means to talk about curvature. So H is a Hermite-Einstein metric. Okay, so I take the curvature, multiplied again by this kind of just normalizing coefficient I over 2 pi. Okay, so what is this? This is a 2 form with values in end E. I can use my Kähler metric to kill the 2 form part by taking the trace to give back a section of end E. I'll tell you in a moment how this is actually defined. That's a section of end E. End E has a natural section, which is just the identity section. And so I can ask that up to scaling by a constant, that this is just the identity section of ND. So these are sections of ND. I mean, I guess some people would write identity on ND here, but one of my collaborators told me that you should never do so because it's only ND that has an identity section. So. Yes. Okay, so I just need to define what this trace operator is, this contraction operator, and then we'll have understood this definition. So where the contraction pi over 2 pi fh, this is a section of ND such that if I multiply it by my volume form, that gives me an NN form with values in ND. This is just up to scaling. The same thing without the trace, but now that's a 1-1 form with values in ND. I want to get back an NN form with values in ND, so I should wedge with omega to the n-1. So this is an operation determined by omega. That's why this omega is involved in the notations. This is like a trace operation using the metric. Okay, so the first point is that lambda is actually topological, i.e., if a solution exists, lambda is independent of the Hermitian metric. It only depends on the topology of the vector bundle. So this is topological. So we can actually calculate what it must be. So if this equation holds, then the integral over x of trace of this thing. Okay, so in general, this integral is the same thing as the integral over x of up to the multiplication by n, I over 2 pi fh wedge omega to the n minus 1. Well, we know that this is a topological invariant. This is the first, it represents the first Chern character of E, whereas omega, again, because it's a closed form, this gives us something topological. So this is like ch1 of E dot the class of omega to the n minus 1. I'm going to write this as alpha to the n minus 1, where so alpha is just the class of omega, and n is the complex dimension of x. Okay, so one of the points of this whole story of Chern-Weil theory, or in fact, Durham or Delbo cohomology, is to extract topological information from integrals of differential geometric objects, and this is just part of that story. Yes? So in particular, what do we get? So you just work out then, if this is true, then what must lambda equal, i.e. what would the number lambda be that makes this plausible? So you just check that this is lambda is n first Chern character of E dot alpha to the n minus 1 over rank of E, because we take a trace, dot alpha to the n. So that's the same thing as the integral of omega to the n, the integral of the natural volume form. This kind of quantity where we have a first Chern character dot alpha to the n minus 1 over rank, it's actually very important in the theory, so we're actually going to give that a name. So for E, even any actual F, holomorphic vector bundle, this may be E, it may not be. We set the slope mu of F to be first Chern character of F dot alpha to the n minus 1 over alpha to the n. So if you're an algebraic geometry, you might like to take alpha to be the first Chern class of an ample line bundle, and these are just algebra geometric intersection numbers in sense in that case. This definition, the slope, this actually makes sense for things that are mildly singular. This is included really just to make the statements accurate. So this makes sense for more general coherent sheaves, actually in very large generality, but I'll just need reflexive sheaves, which are kind of easy to make sense of. This also makes sense for reflexive. They have sheaves, these are coherent sheaves that in particular have singularities. They're not a vector bundle, just on a codimension 2 locus. One can define it in that case just by saying, declaring that it agrees with the first Chern character of the determinant, for example. Okay. So E is slope, E is, so I said slope stability, it's an algebra geometric notion related to numerical inequalities involving subbundles or more generally reflexive subsheaves. So it's slope semi-stable. If for F sitting inside E, this is a reflexive subsheaf of my vector bundle E, the slope of F has to be less than or equal to the slope of E. So this is a numerical inequality, but for all possible subsheaves, and indeed there are a lot of them, so that's what makes this condition kind of subtle. Slope stable. If for all F a proper subsheaf reflexive, so F is not equal to E, we have strict inequality. And one more, slope polystable. This basically means a slight refinement of slope semi-stability that's a generalization of slope stability. So if E is a direct sum of E1 up to EL, where EL are slope stable with the same slope. So that's required to make sure that polystable implies semi-stable of the same slope. So this is slope. Oh yeah, sorry, I'm too involved in the Kähler manifolds picture. Okay, so I'm just going to state the Hitchin-Kobayashi correspondence, and then that will be the end of the talk. I presume that bell is supposed to signify that. Sorry, okay, yeah, sorry, yeah. Yeah. Okay. So it helps that I'm not really going to prove anything in this course. These technical details are not going to be so important. Yes, okay, thanks. Okay, so theorem. Due to Narasimhan and Seshadri in over Riemann surfaces, so dimension 1, Donaldson in dimension 2, Uhlenbeck, Yao for general compact Kähler manifolds, and then Donaldson again for projective manifolds. It says that E is slope polystable if and only if E admits a Hermite-Einstein metric. So you view this Hermite-Einstein condition as a geometric PDE for a Hermitian metric on a vector bundle because it involves derivatives. And then the claim is that you get a natural choice of Hermitian metric, a canonical one solving a geometric PDE, precisely when this condition here holds, which only involves the algebraic geometry of the vector bundle itself. So that's the end of the first talks. Thanks for listening.
Any questions? Questions, comments? I actually had a question. Maybe I'm jumping ahead to your later talks, but so you mentioned mirror symmetry and also the large volume limit and so on. So I was wondering, is there like a, have you thought about if you replace complex numbers by some non-Archimedean field, like the Novikov field, for example? You're taking.
So you might like, for example, geometrically like a degeneration of, I don't know, Claviaus or something?
Right.
Yeah, so that's a really good question. People are thinking about this. I have thought about this. I didn't really get anywhere. So you can ask, I mean, one of the things that people do is suppose you've got a degeneration of Claviaus, then in some sense you can say that, okay, the fibers of Claviau metrics, they're degenerating to some non-Archimedean information, which is a solution of the non-Archimedean Claviau equation. So I tried and failed to set up a theory of these said critical connections for a degeneration of something like a degeneration of Claviaus with a degeneration of vector bundles over them. Yeah, I mean, it makes sense. Exactly what a Hitchin-Kobayashi correspondence would mean in that setting is also something where, yeah, I mean, for the analogous theory of manifolds, Remy Rabelais wrote a thesis that was sort of trying to set up some foundations of those ideas. But yeah, it's an open question, and I think people are working on it. But yeah, it seems too hard for now for me. But I think it's kind of promising.
Maybe a comment in this direction. So, you know, we have this with Haydn, Katsakov, and Kontsevich, we have this kind of attempt to develop this theory for categories.
Yeah.
And there, somehow our motivation comes, not motivation, but the heuristics rather, is often motivated by Fukaya categories.
Yeah,
and
absolutely.
the A side, not so much the, I mean, there is a complex geometry picture by mirror symmetry, but the equations and so on come from there. So I was wondering, and also the non-Archimedean geometry, natural there because the Fukaya category is defined over a non-Archimedean field. And in fact, yeah, there is some kind of Kobayashi-Hitchin type correspondence you can write down for, at least in simple cases like quivers, categories of representations of quivers. So there you get something you could consider a Hitchin-Kobayashi.
Yeah. So of course, I didn't have a chance to mention all of the great work that has preceded a lot of the things that I'm saying. And in particular, this is all living in complex geometry. On the A side, I mean, there has been more done, at least I guess by you, but in low dimensions. And the questions make sense. And I mean, In some sense, what will be a little bit more apparent tomorrow is, although I'm in this setting, some of the ideas that I'm trying to develop should apply very generally. I don't think anyone has tried to apply them to A-side mathematics, but it looks to me like it seems plausible to do so. Just, yeah, there's lots to do. Yeah.
Any other questions?
So in your definition of a slope polystable vector bundle, you were saying that we need the slopes to be the same for it to imply slope semi-stability. What happens if the slopes are different in a direct product?
Well, I guess I know who this is. I mean, you're asking a question by analogy with the theory of compact Kähler manifolds, I guess. You should imagine that direct sum of things with different slopes is analogous to extremal or relatively stable in the manifold side. So it just means that you're a critical point of the norm squared of the moment map rather than a zero of the moment map. So it's directly analogous to extremal Kähler metrics in Kähler geometry. Yeah. If that answers the question.
Yeah, it does. Thank you.
Hi.
Hi.
In your definition of semi-stable, stable everywhere, we require F to be a reflexive sheaf.
Yeah.
What if we remove that and just put bundles?
Yeah, I mean, if you don't, then you can take the reflexive hull and that will preserve the slope. And so it's not really a big restriction. Pedagogically, the point is that for reflexive things, I guess it's probably kind of convincing if I say, I want to define the first Turing character and I just define it to be the first Turing character of the determinant of the bundle, the reflexive sheaf, because that becomes a line bundle then. And we know what CH1 of a line bundle is. So it was really just for pedagogical reasons to assume reflexive. It's not so important. In fact, one can define Turing characters for arbitrary coherent sheaves by taking a resolution and using some kind of alternating sum construction. Yeah, so yeah, if you don't, you can show that this is equivalent by taking the reflexive hull because E itself is reflexive. Yeah.
No, but what if we just consider F to be bundles? Like not necessarily, like they have to be locally free. What happens in that case?
So which are we asking about, E or F?
F.
Yeah, I mean, if F is not locally free, I mean, that's fine, basically. Yeah, I mean, you just need to make sense of what this condition is. And you need to be a little bit careful about when you impose equality here. The point is, if you've got a non-locally free sheaf that is not reflexive, then you can take the reflexive hull. And then the reflexive hull of F will have the same slope as F. And so it doesn't actually matter for the purposes of this. Once you make sense of what CH1 of F means when F is not reflexive. So yeah, that's what I mean when I say it's really pedagogical. One can write down a definition that makes sense in general. I mean, but for example, like suppose F is a subsheaf supported on a curve inside a projective surface, then you need to be a little bit careful about what you mean by the rank kind of condition you impose there. But one can do this. It's done in the Weybrecht's Lane book, for example.
Thank you.
Okay, so does slope semi-stability say anything about a matrix that E can admit?
Yeah, that's a great question. So what you should imagine is that slope semi-stable means you're a small deformation of a polystable generation. So metrically what's happening is you can find Hermitian metrics such that, so maybe it's easiest to write it down, but you can find metrics such that the L2 norm so there's a natural L2 norm using the Kähler metric, and just you take a reference metric, for example, to define a Hermitian metric on sections of ND. But you can find, so if E is slope semi-stable, then you can find a sequence of Hermitian metrics such that this tends to 0. Yeah. So it's sort of like you can approximately solve your equation, but you can't genuinely solve your equation. The point is that these Hermitian metrics, they're converging something that doesn't live on E itself, rather it lives on some other reflexive sheaf, which is the polystable. Yeah, so to a semi-stable thing, you can kind of canonically associate a polystable thing. Yeah.
Any other questions? If not, let's thank Rui again.